I'm going to use this video to introduce a new approach to solving a work calculation. And it's actually a topic that we could have introduced back in kinematics. It's often done, it's included in most college level textbooks, but I thought it was a little too early to throw another type of calculus at you when most of you are still in the process of learning about derivatives for the first time. So there's another, you might call it half of calculus, that's called integral calculus or integration. And I'll spend more time in class like describing this and giving you practice with it, but I wanted to use this video just to show you the nuts and bolts and to show you the kind of problem that we would work using integration. So you see it here, it's a work calculation. So if you've done some work problems already, you know that kind of the basic equation, probably the simplest form, is something like this. Work is done when you have a force acting on something while that object is moving through some displacement. And so what we do here is we take that force and we multiply it by however much displacement, and then we often have to deal with a directional thing. So work is only done by the force that is parallel to the displacement. So we have the dot product that accounts for any angle that might be between them. Now I'm going to not involve the dot product in this problem here. That's just another aspect. So I'm going to have a force that is in the x direction only. So this is just an x directed force. But notice here, instead of a number like 50 newtons, I have a function. And that function is not with time, how we often see functions at this point in the course, but it's based on position. So this would be an oddball kind of a thing where you get a different amount of force based on where you are. Now that's not as unusual as it might sound. Magnets work that way. There's stronger forces when you're closer. The electrostatic forces work that way. Gravity works that way. Springs work that way. Those are the main ones, but this is just an even odder situation than that. And I just totally made up this function for the point of illustration. So here's the force as we describe it. So what we could do is plug in a value of x, and we would figure out how hard this object was being pushed or pulled. And then we're going to describe the object moving between 2 meters and 5 meters. So this is just nice x-directed motion. So moving along a horizontal axis, if you want to picture it that way, and the force is changing. So that means we don't have a number here to throw in for force, because if we did, that'd be easy. Throw in the number, multiply it by, what do we have here, 3 meters worth of motion, and this is a pretty simple problem. But we cannot use that. So I'll say not if in, let's say I better not describe it that way. How about this? Not if a changing force. Because we have a changing force, we're not going to be able to use this. So instead, we're going to use a form of the work equation that involves maybe some symbols you haven't seen before. I just want to decipher what this is. Still has the dot product in it, which again, I'll kind of ignore for now. But what this means is this dx here is just like delta x in the previous equation, but it's a really, really tiny, like infinitesimally tiny little delta x. So we use the letter d rather than the Greek letter delta. And here we have our force. Again, that's going to be some function of x, and I'll just put a little x there to remind us that it's only in the x direction. And then this means, it's the letter s, it's actually a kind of an elongated s, it means the sum of a whole bunch of little work calculations. So if we take a bunch of tiny little steps and we measure the work done just during that tiny little step, for that little step we can actually imagine using just a single value for the force. So if we do that for each little step and then sum together, that's what the S means, sum together all the little work values, we might call them worklets, if you will, tiny little work values, then we will get the total work done over that entire amount of motion. So that's what this equation means. On the AP reference sheet, it's written very similarly. It's right up here, equation number 9. But it's written, instead of with an x, it's written with an r, because r is a little bit more generic. So this could be done in the y direction or It could be done in like a radial direction, outward, inward, z direction. So the r is a little bit more generic, but we're just dealing with the x direction in this problem here. So here's what the mechanics of this actually look like. So what you do is you write the equation first, just like that. I'm going to leave the dot product and the vector symbols out in the next step because we really don't need it. So what I'm going to do is I'm going to substitute in my function. And this is the function that you were given in the problem. And I like to put it in parentheses, just so it kind of sticks out by itself there. And then I write dx again. Dx, again, remember, is taking the place of the delta x. And then what we do is on the s over here, and we say we're going to sum up all the little worklet values, we have to put in over what range or what limits this work is going to be calculated. So it's just the lowest x that you have. So here the lowest x is when x equals 2. And the highest x goes up here when x equals 5, which is actually your initial value and your final value for what x is going to be. So that's how we set it up. Now at this point, someday in calculus, you'll learn that this is a pretty routine problem. But how do you actually solve the problem? There's a number in here somewhere, and I just want to show you how we get to that number. So the first step is we do what's called the antiderivative step. So the idea is this. There's some function that we're looking for whose derivative is this function here, our force function. Now you know enough about derivatives, I hope at this point, that you could kind of work backwards and say, well, what function could I start with and then take the derivative with respect to x and get this function out? So it's a lot easier to recognize it after somebody does it, but I always put mine in little brackets here when we do this. So that function would be 5/4 x to the 4th minus 3/2 x squared plus 8x. And I always recommend for students that are new to calculus, just make sure that you go back and take the derivative of this and be sure you get the function that we want there. Okay? There's actually other functions that will give this as a derivative, but this is the one I think you could recognize most obviously. All right, so we've gotten rid of the s. I've put my new antiderivative function here in brackets, and now I put my limits over here on the right side. It seems a little strange, I know, but that's just kind of how calculus people do it, and physics people also. So now what? Well, now what we do is we plug our upper, we'll call it the upper bound or the upper limit, or our final x value into this function here. So this would be 5/4 times 5 to the 4th. All I did was put 5 in for x. And then minus 3/2 times 5 squared plus 8 times 5. So x took the value of 5 for all of those. And then I'm also going to do it for x equals 2. Hopefully I can squeeze it in here. 5/4 times 2 to the 4th minus 3/2 times 2 squared plus 8 times 2. So those two are some numbers that we could calculate, and then we subtract it in that order. So we evaluate it at the upper limit, and then evaluate it at the lower, and then we subtract upper minus lower. So I did this earlier on my calculator, and I got, this is 783.75 minus 30, which means our final work value would be what? 753.75. And since this was in newtons, the force in newtons, and my displacement was in meters, I can say that work is in joules. So that's the mechanics of finding work using integration. And again, when is it necessary? When we don't have a single number that we can just put in place of a force, so many newtons. We have instead a function that changes as the thing moves. So rewatch this as necessary if you get one of these and you're having trouble solving it. And of course, we'll expand on this a little bit more during class, but hopefully this gets you through these kinds of work problems without too much difficulty. Thanks for watching.